Thanks, Kai, for recording service. Hello everyone. Welcome back to today's Future Intelligence Talk session. We are glad to invite Michal Piovarci from ETH Zurich to give the short talk. Before his talk, let me just brief introduction, give you guys an introduction. Dr. Michal Piovarci is postdoc in ETH Zurich in the Computational Design Lab, led by Bernd Bickel. Previously, he was a postdoc at ISTA in the Visual Computing Group. He obtained his PhD at USI Lugana in 2020. His thesis entitled Perception-Aware Computational Fabrication received the prestigious Eurographics PhD award. His research broadly include computer graphics, computational fabrication, haptic reproduction, appearance reproduction, and perception. Okay, Michal, over to you.
Good afternoon, and thank you for the kind introduction. And also thank you for giving me the opportunity to talk here today about my research. And today I will show you how we can break the limitations of fabrication devices. However, before that, we should look at what are the capabilities of modern fabrication. In recent years, we have seen rapid advancement of manufacturing, and novel methods enabled us to realize high-precision prototype, create prosthetics, first artificial organs, and even produce parts with improved behavior, such as stiff yet very light airplane parts. And the main driving factor behind this improvement is the development of additive manufacturing. By designing where the material is deposited, one can achieve unprecedented levels of object complexity. And this complexity can in turn be leveraged for personalization of the fabricated parts that can be manufactured on demand and based on the individual needs. Unfortunately, not all objects can be created equal. I generated this visionary novel musical instrument using ChatGPT. However, before we can produce such an object, we need to address many open questions like, can we match the geometry of this model? What material is it made of? Can we produce with such a material? And the answer to these questions is, in most cases, no. Current fabrication devices do not have sufficient resolution to mimic arbitrary level of details. We are also unlikely to possess exact envisioned materials that ChatGPT was thinking we are going to use. However, the quick questions for today is, do we need to exactly match the reproduction to create a realistic instrument? Because the ultimate purpose of this object was to play some sound. So let's focus on the functional part and rephrase the question. Can we leverage the capabilities of fabrication devices to create a functioning novel musical instrument? So to answer this question, we should investigate how fabrication devices work. A common manufacturing device is characterized by the ability to deposit a wide range of materials. And moreover, the deposition happens at very high spatial frequencies, which allows us to control with micron precision where in the 3D space a particular material is deposited. The task of fabricating an object then reduces to a combinatorial search where we seek to find an optimal material for each spatial location. Unfortunately, we can see that even this example with 3 materials and 4 material slots leads to 81 possible combinations. And therefore, for realistic problems, they often lie on combinatorial spaces that are simply too vast to manually explore for a human designer. So to facilitate the design, even in such challenging scenarios, we rely on so-called computational fabrication. And computational fabrication is a goal-driven process. On the input, we typically have a geometry that we want to manufacture and a goal behavior we seek, such as, for example, the sound that it should emit. And to find the optimal material assignment, we rely on optimization. To keep the problem tractable, we reduce the dimensionality with a suitable parametric design. Then we assign materials to the parametrization and using physics-based simulation, estimate the expected physical properties. Finally, we evaluate how far we are from the target, and this error measure is what drives the optimization forward by updating the parametric design. And it is this last step where we need to consider the printer limitations that emerge. We need to make sure that the adjustments to the design we propose utilize the materials that are available to the device, follow valid movement trajectories, and in the end, produce a valid printout. And it is this need to fit within the physical constraints that drives the hardware improvement cycle. We start with a fabrication device and implement its constraints within numerical algorithms to get most value out of the device. And when we hit the computational limitations, we collect the knowledge and from the optimization process, from the printouts, and try to improve the hardware. However, at the core of this process are human designers. The engineers that build the hardware, the material scientists that design the materials, and the computer scientists that produce the optimization software. And the core question is, can these humans in the loop actually predict and propose optimal designs? And this is what I would like to talk today, and to not show you yet another hand-tuned hardware design or optimization loop tailored to a specific problem. Instead, I want to investigate the option of systematically exploring the printing policies of fabrication devices to achieve a given task, to propose a single unified framework for discovery of printing strategies in which problem-solving behavior naturally emerges on its own. And to this end, I will present you two projects. In the first project, I will introduce our framework and demonstrate how smart control of the position devices can enable printing with materials before considered non-printable. And next, I will show you how the framework can be generalized to exploration of highly nonlinear design spaces. I will demonstrate that through systematic exploration of the design space, it's possible to take something history considered as a disadvantage, the high nonlinearity of them, and turn them into an advantage. So let us start with the first project, where we intend to deposit a wider range of materials. To achieve this goal, we enhanced a 3D printer with a set of eyes, which is cameras, to allow self-monitoring and on-the-fly adjustment of the printing strategy. And as the main challenge, we picked materials with low viscosity. Such materials have high appeal in manufacturing, in either biocompatible or production-ready parts. Unfortunately, they are commonly regarded as impossible to print. And to understand why, I made an example where I deposited a silicon material, and you can observe how the material spreads after the deposition. And this spread is actually highly dependent on the rheological properties, but also on the local geometry of the deposition. And this is what made scientists before assume that this cannot be effectively corrected for, and such a material is not suitable for manufacturing. And to achieve a system that deposits this material and corrects for any material flow, we will leverage this new set of eyes that we gave to the printer. We wanted to build a control policy that affects the machine parameters that control the device. And by observing the position, we will then see how well we are doing and update the control parameters accordingly. Unfortunately, to learn from experience, we need to interact with the physical hardware. And that is very, very slow to be practical. You can now see the printing head in the image moving, which is the actual printing speed that the device can achieve. And that clearly shows that it is not possible to generate a vast set of samples from which we could learn the behavior. So instead, we developed a numerical approximation of the deposition, where we had a system with an artificial printing head that was depositing the material. And to ensure that the simulated deposition matches with reality, we observed actual material paths over several depositions. And in this example printout, you can see that the width of the material is not constant, but changes over time. And this is a result of utilizing non-optimized materials that exhibit inconsistencies during prints, materials which are also curing over time and are becoming thicker and thicker as we deposit them. So constant deposition will not achieve constant results. And we collected all of this knowledge and brought this behavior back into our numerical simulator by proposing a generative model for the printed behavior. So a generative model varied the deposition output similarly to a real device and can be further fine-tuned to provide a rich training space. And here you can see our simulated printing head in action. And by interacting with the simulator, our control policy can train over millions of iterations and achieve stable behavior. So we can now take a look at some results. When we execute our policy on physical hardware, you can see two deposited shapes. And when we zoom in, I marked an area of interest. We can see that our deposition, which is marked with green lines of the intended target, is significantly closer to the boundary where it should be. It's actually almost perfectly matching, whereas a direct printout without a controlled policy has a very significant over-deposition, which is caused exactly by the variations of printing that are emerging during the material use. So I would like to stop here and highlight the first key observation of this talk. We took a material that was considered impossible to print, and we modified only our deposition strategy, did not touch the hardware, did not touch the material. Yet, we enabled a high-resolution deposition. And this shows that careful exploration of the control space enables to break through the before believed hardware constraint. Because in the past, when you would saw such a deposition, you would actually go back to your material scientist to design you a new material. Instead, we demonstrate that the limitation was not in the hardware, but in the way we were controlling the machine itself. So now I would like to take this concept one step further. In computer science, we often hear that if something is nonlinear, it's very challenging to solve. However, can we leverage learning to turn this disadvantage into an advantage? Can we see a nonlinear design space as an opportunity for exploration? So imagine if we would like to produce this beautiful color painting on a 3D printer. The method of choice for now is so-called inkjet printing. An inkjet printer has a series of printing heads, one per each color. And when we deposit a material, it individually fires from the nozzle and creates a standalone color. So then if we fire multiple materials, we get a nice clean transition, which is critical for high resolution color printing. However, there are also alternative printing techniques that are significantly more accessible cost-wise to a wider range of public. And the catch is they cannot deposit individual colors. Instead, they rely on a mixer that mixes the material as they go in. And this results in a smooth transition, which is undesirable because it reduces the optical resolution of the final image. So the question that we ask is there something that we can do to improve the color reproduction on systems with smooth color transitions? To achieve this goal, we will take advantage of two phenomena. So the first one is nonlinear mixing of color inks. Where we mix two inks, you can see on the left, the resulting color is a nonlinear combination of the original pigments. We can contrast this with commercial software that relies on linear mixing and as such does not match the colors of real paints. It is a well-known yet very challenging effect to model, and only in recent years we have seen some first real-time predictors of color mixing. So the first component that we have is that a relatively small change in the pigment ratios can have a significant effect on the final mixed color. So please remember, in the past works, this was considered a key challenge to overcome, and during modeling, as including these nonlinearities in hand-designed prediction models is highly non-trivial. And the second component relies on exploring how our eyes perceive color. All colors we observe are in fact electromagnetic radiation emitted towards our eyes. And as an electromagnetic wave, we can describe each color as a decomposition of the individual wavelengths. This is known as spectral or true colors. And to perceive these colors, our eyes possess cones that are sensitive to blue, green, and red light. While we refer to them with such simplified names, the colors only marks the peak sensitivity of each receptor, and in practice, the individual receptors are sensitive to a range of wavelengths centered around the primary color. So let us now focus on the blue cone. To estimate the intensity of the visible blue color, our eyes integrate the reflected light within their sensitive region. As a result, two different spectral colors can appear to be the same as long as the area under their spectral curve integrates to the same number. And if you remember, we can significantly alter the visible color of a pigment mixture just with a minor variation. So our goal now is to find a way to exploit the color metamerism by pre-processing the colors within their allowable perceptual range to allow a quicker transition to a new color. And to handle this problem, we adapted the learning framework with a new simulation to perform a desired material change, which would be a straight step function. We first simulate the physical delay of material pouring into the mixing unit, and then a smooth change of material as the mixer deposits its contents. And here we can see the results. On the left is a direct printout from the color printer without our method, and we can see significant ghosting, what is the result of not taking into account the material change. Moreover, we can see that it has a significantly lower resolution and lower contrast. In contrast, our control policy adapts the material on the fly and leverages the nonlinearities in color mixing to produce a nice, clean image. So I'd like to stop here again to highlight this second observation, that by systematically exploring the design space, we can propose printing policies that leverage the nonlinearities of the problem domain. What was before a challenge, navigating the nonlinear space, now becomes a feature that enables us to push beyond what was considered the best achievable print beforehand. And to recapitulate, so far we have seen that learning has a wide impact across fabrication. It enables more efficient use of current hardware and materials through smart adjustments to the printing parameters on the fly. And it enables us to explore complex design spaces and optimal trade-offs in a principled manner. So for the remaining of the time, I would like to take a step back to see how is learning overall affecting the landscape of fabrication. To this end, we need one last technical term. Imagine that the white portion of this slide represents all the objects in the world. When we have a 3D printer, it can typically produce only a limited number of objects, and we will denote these as the gamut of the printer. And of course, as we add more fabrication devices, our gamut of what we can manufacture expands. And eventually, we can see that make a fence around all the objects that we fabricate. Such a view allows us to see the learning-based methodology within context. Currently, we utilize learning to create more intelligent hardware that is capable of processing a wider range of materials and exploring some nonlinear design spaces. I believe that in the coming years, the utilization of artificial intelligence in manufacturing will accelerate, and eventually will not only provide incremental improvements, but crystallize into a separate fabrication endeavor. And I believe that this will lead to a truly transformative change of fabrication. Instead of having separate stages of machine, material, and algorithm design, we'll observe a single unified pipeline that optimizes all components jointly in an end-to-end fashion to achieve a target functional behavior. So finally, to conclude, I hope I persuaded you today about the benefits of artificial intelligence for fabrication, mainly the ability to lift hardware limitations to process a wider range of materials with current machines, and the ability to navigate complex domain spaces and leverage their inherent nonlinearities to produce better printouts. And with that, I would like to thank you for your attention. And I would also like to thank all of my collaborators, without which I would not be where I am today.
Thank you very much, Michal, for the great talk. Let's see if our audience has some questions. If any questions, can just let in the chat room, or can just speak out. Okay. If we don't have any questions, let me probably start the question then. So you've introduced the learning-based method for improve the fabrication capability, right? So my understanding is that you need to train the model, a control policy before you actually implement it. So is the trained model applied to some benchmark shapes, or actually it's kind of universal to different geometries? That's my understanding.
So the model is applied on some shapes, and you need a data set. Depending on the specific subproblem, the size of the data set will also vary. So for example, in the first project, we were specifically trying to reproduce single slices. And in that case, you need a significantly varied data set of individual slices to be able to include sharp features, smooth features, straight lines. Because if something like this would miss from the data set, we actually found out it cannot generalize as well as something which would be, for example, physics-driven, which would have the inherent knowledge that if I have a sharp turn and I don't slow down beforehand, it will overshoot. So the training needed to really have specific examples of these things and needed to explore them, need to experience them to learn how to behave in such situations. However, the design space or the spaces can be significantly reduced. So in the second project, we were only looking at a single line of each image. So in fact, it was sufficient to have about 10 images to train this predictor. We again needed a variety of colors, but in principle didn't need many images themselves.
Okay. And further to that question, do you think that we probably need a public data set for training as a asset for fabrication improvement, something like that?
So public datasets are generally nice. The one catch with the fabrication devices is that they are quite specific, and it's sometimes very hard to transfer the knowledge. And you would need at least certain levels of abstractions because it depends on how deep you want to go into the rabbit hole. You can, of course, get the maximum control if you directly control the individual motors, but then this becomes really a controller trained only for a particular machine with a particular brand of motors. And you can then go a bit step up and step up, but still there remains the challenge that different hardware devices will behave a little bit differently.
Yes.
An entire synthetic dataset would be nice, so people could actually experience with different ways of learning these controllers without having to invest into the hardware itself, because currently that's a really big block. If you want to perform a similar research, you would actually have to build the hardware as like we did, and not many people are simultaneous mechanical engineers and computer scientists.
And I also think that the material wise, I mean, material side and also the process itself involve different machines will have impact on that, right? Because you are proposing, I think there's a fusion, sorry, the deposition based, extrusion and deposition based thing, right? And there are others, surely there are other process for additive manufacturing and other fabrication process.
Yes.
I think, yeah, that will be some interesting work in the future. Thank you very much. So yeah, if can I ask if still any questions from audience? If not, I think we can close today's session. And thank you again for today's talk, Michal. Let's keep in touch, and I hopefully we can see you face to face again in the future. Thank you.
Thank you as well. Have a nice day. Bye bye.
Bye bye.